I'm going to start with part one of our forces and Newton's three laws. Now, this is going to be a little bit of a long video because this has got to cover a good amount of stuff that you should have learned in physical science. So let's get rocking and rolling. Not this. What's a force? Not this, but sort of. It's kind of like that whole deal. Like you may have been like this as a kid, or you may have been laying on the couch and been like, "Hey, come on, remote," and you're like reaching, hoping that remote moves. Well, that's not going to happen. Okay. It can't happen because if you look at all these assessments and statements and stuff, force, which is variable F, a force is a push or pull on an object. And the unit for it is a Newton. Okay. Why did it come up with Newton? Because Sir Isaac Newton. Okay. So a force is a push or pull on an object. So right here, you should have known that. What is the term net force? Net force is the sigma force. Okay, sometimes we call it the sigma force. It is the total. Okay, and you're going to notice the words balanced and unbalanced. We'll cover that here in a little bit. And this is called something a force diagram. And a force diagram is, we've kind of seen these before when we talked about vectors. They're going to have direction, they're going to have magnitude, and we got to do a little math with them. A force is a push or pull on an object that on one object exerts on another, hitting a baseball, throwing a basketball. Some forces aren't always noticeable. Think about that for a second. Yeah, some of you might be thinking like, wait a minute, if I sit perfectly still, somebody told me once, if I'm sitting perfectly still in my chair, I'm still moving around the universe at 10, 20,000 miles per hour. Well, that's absolutely correct. We've talked about earlier in class about um, if you were sitting still or falling asleep in a car, somebody watches you go at 70 miles per hour by them. Well, one that we never think about is that gravity is pulling down on us, but the floor is actually pushing up on us. And forces influence motion, changes the velocity, speed, or direction. So again, when you think about it, the box sitting on the floor here, the force of the earth acting on the box, it's weight, but the force of the floor acting up on the box. And they have to be equal but opposite. We know that because the box isn't moving. If all of a sudden the box shot up in the air, then we'd say that the normal force, or the force upwards, is greater. If the box fell through the floor, then we'd say the force of gravity is greater. Okay? Net force is the total force on an object. If the forces are balanced, no movement occurs and net force is zero. Balanced forces. Forces are equal in size but in opposite directions. Why don't we fall through the floor? Well, again, because those forces up and down were balanced. Unbalanced forces. A force that is not balanced by another force. It results in movement. So for example, over here, our total force is unbalanced. So we have movement. The forces add. Okay, these forces are balanced in opposite directions. So our net force is zero. So the forces cancel. We would say most of the time there is no movement here. So for example, right here, we're not going to have any movement. We have four forces acting on this rock. It's not a baby carriage, it's a rock. Okay, we have the force of friction that counteracts the force applied. There's the normal force, which is the force we usually don't feel, and the force of gravity pulling down. Different than this picture right here, where the applied force is now greater, so our motion would be, or our net force would be to the right, and that net force, we'd be saying that we're moving in the right direction. Here's just some examples of slides that do the math of this. Again, I'm going through kind of quickly because this is a long section of notes, but I want to make sure that if you need to go back and look at it, go ahead and pause and you can look at these things. And for all my math people, it's very easy to kind of see how that's all broken out. These are all available as well in the traditional notes that are attached. What is a Newton? So we say, what is a Newton? Well, one Newton is approximately 1/4 of a pound being pulled down by gravity on Earth. That'd be like an apple, a couple golf balls, two big D-cell batteries would be about what a Newton is. Weight versus mass. This is a huge deal. Weight is the gravitational force exerted on an object. Weight decreases as an object moves away from the earth because gravity decreases. Weight results from a force. Mass is how much matter an object contains. So we have little Jimmy here. Jimmy is on Earth and he's on the moon. Let's just say his mass, if we measured Jimmy's mass, his mass was 10 kilograms. Well, his mass on Earth is 10 kilograms, and his mass on the moon is 10 kilograms. He didn't lose arms. Mass is how much matter an object has. It would be really hard to find astronauts if we said, hey, when you go to the moon, you're going to lose a couple arms and legs. Wouldn't work out. Most people wouldn't sign up. His weight on Earth, though, would be 100 newtons. His weight on the moon would be 16.6 newtons because the gravity on the moon is less. It's actually, the moon is 1/6 the size of Earth. So that means gravity is 1/6 that of Earth. So that's why his weight is 1/6 of what it is on Earth. So if you have a weight problem, you go to the moon. You'll drop weight instantaneously, no problem. Step on that bathroom scale, weight's going to drop. But you're really not going to lose any mass because you still have the same amount of matter. Now, Jupiter is larger than Earth, so it has a greater gravity than Earth. So our weight on Jupiter wouldn't be 100. Our weight on Jupiter would be, I don't even know, 2,000, 3,000. Okay? But our mass would still be the same. Real quick, Newton's 3 laws of motion. Newton's first law of motion is inertia. Inertia is a property in objects is the property of an object that resists a change in motion. Things are lazy. Things want to keep on doing what they're doing. Now, things that aren't moving, that's easy. Like to go push this bus would take a lot of force. But once we got that bus moving, it'd be really hard to stop it. You've probably seen people like trying to push a car, and then they get it moving downhill, and they have to run back in front, and it's really hard to stop. It's because an object wants to keep on doing what it's already doing. So an object in motion will stay in motion, an object at rest will stay at rest unless acted on by an outside force. The more mass, the more inertia, because it requires more force to get it going, but it will also require a larger force to make it stop. Things keep moving or stay at rest unless a net force acts upon them. Again, here's our little dude. Boom, there he goes. Skateboard stops. But again, you continue to move forward. You might have an accident. Okay, you've probably all been in a car, something sitting on the front seat, slam on the brakes. My mom once had a casserole go all over the front of the car because it came right off the front seat. Boom. Well, it didn't shoot off the front seat. There's no spring in our front seat launching it. It's because that casserole is still moving in motion. Well, this happens all the time with cars. Okay. You've all experienced this one time or another. Somebody cut you off, or maybe you've been in an accident and you have felt your body continue to move forward. It's not like there's an ejector seat button that launched you forward. Okay. So injury is directly related to inertia. In car crashes, you tend to remain in motion unless you're acted on by a force, unless something resists you. Well, hopefully you have your seatbelt on. If not, where the injury occurs is something is going to stop your motion. Either the windshield, ejected from the car, you hit a tree, another, that's when people die. Okay. We have seatbelts because seatbelts, okay, provide an unbalanced force back at you. Well, many of you probably don't even know how a seatbelt works. Well, this is the old school way, but it's pretty much the same, except this block down here has been replaced with electronics. But the whole point is pretty much the same. When you come to a large stop very quickly, this block moves forward, which had a little bar that hit the pin in the pulley. The pulley is what's in the wall. You can hear it when you pull on your seatbelt. It's moving up or down. Well, it locks, right? When that hits, it locks. The seatbelt doesn't move forward anymore, and you've all felt the seatbelt like almost choking you out. How do you relieve that tension of the seatbelt? Well, you can't pull it out anymore. So someone usually has to take their foot off the brake and can start driving. Well, the block slides back, releases the pin, and then you're able to move. Newton's second law, F equals ma. So I always used to say, what would you never say to your mom? Well, what the F, ma? Okay, F equals ma. The whole relationship between mass and acceleration. The whole idea that if our mass stays the same, to get a larger force, we'd have to accelerate that mass faster. Okay, and that's kind of what all this is. That's why if you if you kick a brick wall with the same force you kick a ball, the brick wall, your toe's going to hurt. Okay. But if you kick the ball, we're having fun. We're playing a game. But it's the same force, different mass, which means different inertias. Okay. cause different accelerations. Again, right there, more mass requires more force. More acceleration requires more force. Again, these next ones are just showing you how to actually do the math and story problems. You'll probably need to pause these, go back and look at them. That's fine. It's just basic math. Feel free to pause, make sure you know what you're doing. Take a second right here and see if you can solve these four. Go ahead and pause the video. All right, hopefully you've looked at these and you've gotten these answers. If you did not get these answers, and don't worry about the units, I just never have changed the units to the proper IB lingo. But as long as you have those answers, you're good. If you did not get those answers, that means you should be asking Mr. Tima for help in class. Newton's third law, this is probably the easiest one. It's probably the most commonly known one, and that is the one for every action, there is an equal and opposite reaction. Okay, the swimmer pushes off the wall, so the wall actually pushes back and allows that swimmer to spring off the wall. You've probably all either slammed into something like the pads in the gym, or if you've ever swam in an above ground pool where you push off the wall to maybe shoot across the pool, well, that wall gives a little bit. Since that wall gives a little bit, we don't have as much of a reaction force. How do rockets move in outer space? Well, it's real simple. There's an explosion. We inject a fuel and we light it on fire, and there's an explosion. The same amount of fire we see on the back end, which is actually not doing anything, this does absolutely nothing, is the same amount of fire that's actually exploding in this direction, which we have these cones that focus that force. And since that amount of fire is coming out this side, there's that amount of fire force on the inside pushing the rocket forward. Okay, here's some other action reaction pairs. This is called a Newtonian cradle. Those balls on a string, you may have seen them move before. Unfortunately, you're not in class, so you can't see this. You may have fired a gun before or a weapon. You know that a gun or a weapon kicks back at you, and that's because there's an explosion. Since this side's open, the bullet flies out. This side kicks back because that same amount of explosion. Here we go. 2 questions. In the top picture, Mike is pulling upon a rope which is attached to the wall. In the bottom picture, Mike is pulling upon a rope which is attached to the elephant. In which case is the force scale read? In each case, this force scale reads 500 newtons. Mike is pulling A, with more force when the rope is attached to the wall. B, with more force when the rope is attached to the elephant. Or C, which you can't see right here, obviously. Or C, the same force in each case. Go ahead and take a guess right now. Hopefully, you've been paying attention, and for every action, there's an equal and opposite reaction. So the answer is the answer is C, the same force in each case. All right, one of the hardest questions in physics. They'd love to ask this one. While driving down the road, a bug strikes the windshield of a bus and makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The bug hits the bus, and the bus hits the bug. Which two forces is greater? The force on the bug or the force on the bus? Again, the bug hits the bus and the bus hits the bug. Which of the two forces is greater? The force on the bug, which splats, or the force on the bus, which continues to move forward? Well, some of you might be thinking, this doesn't sound right. There's got to be something going on here. Well, you're right. It is a trick question. For each force is the same size. For every action, there is an equal and opposite reaction. The fact that the bug splatters only means that it has a smaller mass. Since it has a smaller mass, it has a smaller inertia, and it can't withstand that change. Okay? Things that have greater masses have a greater inertia and can withstand a change in force greater. Okay? That's why small kids that play football tend to get hurt worse than big kids that play football because their mass is less. They can't take the same hit, okay, that someone else can. But then how in the world could you ever drive a nail into a wall? Because if I hit a nail with 10 newtons of force, the nail is hitting me with 10 newtons of force. Okay? Well, then why don't they just hit and stop? Well, if it was a flat nail, if the bottom was flat and blunt, as we call it, then the nail wouldn't go in. You probably had like a bent tack and couldn't get it in there. Okay? Well, if you've ever looked at the bottom of a nail, it has a really sharp point. Since it has a really sharp point, what we've basically done is reduce the mass at the point of contact. And since we reduced the mass, that means the inertia has gone way down. And since that inertia has gone way down, then we can then puncture or put that inertia through that wall. All right, we're going to watch this little movie real quick here. What if there was what if we had no gravity on Earth? What would that look like? So this is an actual NASA video. Okay, it's pretty cool. It's going to take a few seconds here.
On March 18th, 1965, Russian cosmonaut Alexei Leonov became the first human to float in space. Not to be outdone, the United States sent astronaut Ed White into outer space just 3 months later.
You're right, Ed. You look beautiful. I feel like $1 million.
He floated for 20 minutes and loved every bit of it. Floating around is fun and easy. The next American would have to do more than just float. Gene Cernan would try to find out if humans could do work in outer space.
I was going to go out and I was going to have to do legitimate work. I had to basically assemble a whole flying backpack outside the spacecraft in zero gravity through a nighttime cycle where I had little or no light.
Cernan was supplied oxygen from an umbilical hose that passed through an open hatch. His commander, Tom Stafford, seated inside, piloted the spacecraft. Cernan quickly discovered that handling even simple objects was extremely difficult.
And every time I'd push or turn a valve, it would turn my entire body in zero gravity. I had nothing to hold on to. And we take for granted gravity because we can do that kind of work with ease if something is holding our feet to the ground. Nothing was holding me anywhere.
Within minutes, Cernan was sweating from the extreme effort it took to control his movements.
Within a few minutes, he fogged over. We were so naive, we didn't even think about putting defog on our visor like you do when you go snorkeling or scuba diving. And so he was huffing and puffing, and I was flying the spacecraft. He says, Tom, I've got a hard time controlling myself.
And it was a very, in retrospect, somewhat of a hair-raising thing. And there were probably times where there were people down here on Earth wondered whether I'd get back in. My heart rate was running at 170 beats a minute.
So this is not a good situation at all. So I called the ground and the contact said, I've called it quits. I'm going to get him back in before we go in the next nighttime. Got him in. Finally, he just couldn't hardly move. And then when he opened his visor, he was absolutely pink, like he'd been in a sauna about an hour too long. The next day we landed and they flew the suit right back to Houston. They had over a pound or a pound and a half of water out of each boot. But he lost, I think, 10 and a half pounds in 2 hours and 5 minutes outside.
NASA was now determined to find out what went wrong.
As engineers, we started saying, look, we've had 3 missions where the EVAs didn't go well. What was wrong? Then we had a science advisory team step in and say, look, your entire principles of EVA are wrong. How you train, how you prepare the crew.
Everybody forgot Newton's third law of motion. To every action, there's an opposite and equal reaction. And when they touched the spacecraft repelled them.
Although weight is reduced in outer space, the mass of an object is unchanged. To move a mass, force must be applied. Newton's third law predicts an equal but opposite reaction. On Earth, Gravity would allow Cernan to gain a footing and counteract the reactive force. But in outer space, the reactive force sent him reeling. Having learned a difficult lesson, NASA's next capsule was built with special handholds and footholds to anchor the astronaut in place. Most importantly, NASA began training astronauts underwater, the closest environment on Earth to weightlessness. The new training and tools made a big difference for Buzz Aldrin, the next American astronaut to do work in outer space.
I felt that it was a piece of cake outside, just moving very slowly. There was no challenge. You decide that you're going to move in a certain way and you need leverage, so you just don't allow yourself to get out of position.
So pretty cool there. Pretty cool. But the whole idea, just the idea to think if you were on Earth right now and you were trying to turn a knob, just trying to turn a knob on a door handle, and if you didn't have any gravity, that you would just start turning opposite like that, like a counterclockwise, if you will. I mean, it's just crazy. So it's crazy to think all that money was spent, and the first thing they forgot about was Newton's